Welcome. The focus of this video is on mechanical work from a change of volume. This is called the boundary work. A number of relations can be developed to correlate the boundary work to pressure, volume, and temperature, depending on specific thermodynamic transformations, especially when the fluid is an ideal gas. These same relations are frequently used to determine the boundary work in thermodynamic cycles too. Let us have a piston cylinder assembly enveloping a mass of gas M and a piston of head area A. A force is applied on the piston to move it from an initial position 1 to a final position 2, achieving a vertical displacement delta H. While the control mass remains constant throughout the transformation, the control volume reduces. In this specific device, we can give two definitions. Pressure can be defined as the limit of the infinitesimal force dF over the infinitesimal area dA as dA approaches zero. The specific volume is clearly the ratio between control volume and control mass. The control mass is constant when the piston moves from position 1 to 2, but not the control volume, which reduces. Given the piston head area A is constant, the infinitesimal change of control volume is A times the infinitesimal change in the vertical position. The infinitesimal change in specific volume of the fluid is therefore the infinitesimal change of the volume A times the dH divided by the constant control mass M. Now we have everything to define the energy spent to reduce the volume of the fluid. This is called external mechanical boundary work. External because it is from an interaction between the system and the surroundings. Mechanical because the piston moves to make the energy exchange to happen. There is no mechanical work if no item moves. Boundary because the energy is exchanged because of a change in the boundary of the control volume. We start from the definition of work, that is the integral of force by infinitesimal displacement. As previously defined, the infinitesimal vertical displacement can be replaced by the ratio between the infinitesimal volume dV and the piston head area A. Pressure is exactly the ratio between force and surface, which leads to an expression for the work as integral between V1 and V2 of PdV. This is the external mechanical boundary work in Joule. Its specific counterpart, written by using small case letter W, is the previous divided by the control mass M. Being M constant, the expression can be written in terms of specific volume. The value of the boundary work depends on the path taken to connect the initial and final states. We call path function all those functions whose value depends on the curve followed to move from one state to another. Let us understand it through an example. Take your time to read it. We have an ideal gas in a piston cylinder assembly, and we want to move from volume A to B. We compare two paths. Path 1 moves through a transformation at constant temperature. Path 2 moves from state A to state C, first through a constant volume transformation and then from C to B through a constant pressure transformation. It is useful to calculate the pressure for all states first, given they are not given. Then the boundary work is obtained for path 1 by solving the integral, and for path 2 simply multiplying the pressure by the change of volume. The boundary works are in both cases the areas under the curves. The comparison between the results show that the boundary work is different. It is the sign that boundary work is a path function, and its value depends on the specific path taken to move from the initial to the final state. A thermodynamic cycle is made by a set of transformations that start and end in the same state. The transformations can progress clockwise, and in this case the cycle is set a direct cycle or anti-clockwise, and in this case the cycle is set reverse cycle. When the transformation progresses from left to right in a PV diagram, there is an expansion and accordingly a generation of work. When instead a transformation progresses from right to left, there is compression and accordingly work must be done onto the system by the surrounding. The difference between all work generated and all work received is called the net work and can be positive, as in direct cycles, or negative, as in reverse cycles. When it is positive, the cycle produces mechanical work, which can be used for multiple purposes, such as electricity production or transportation. When it is negative, the cycle needs energy from the surrounding, which could be in form of heat removal for cooling purposes, for example. A transformation can go in the PV diagram in very diverse ways, but there are some common transformations, which are most frequently followed in practical engineering devices, such as in the piston cylinder assembly. Compression and expansions are ubiquitous in engineering devices. Therefore, our first focus is to find a way to calculate the work when an expansion or a compression happens. Real engineering devices realize compressions or expansions that are sketched in the PV diagram through the general correlation P times V to the power of n equals constant. This is called the polytropic transformation, and the exponent n depends on the combination of the particular design of the device that performs the compression or expansion and the operating fluid. Except special cases, such as a transformation with no change of temperature, the exponent n is determined empirically. Polytropic transformation of ideal gases can be expressed in alternative ways, replacing the PV pair with the TV or PT pairs. In specific problems, it could be more convenient to use one expression than another. In a polytropic transformation, the exponent n can vary between two extremes, 0 and infinite. When the exponent n is infinite, the polytropic transformation is one isochord, that is a vertical segment, in the PV diagram. When the exponent n is 0, the polytropic transformation is one isobar, that is a horizontal segment, in the PV diagram. For any other intermediate value of the exponent n between 0 and infinite, the transformation is nonlinear. Depending on the value of n and whether the fluid is an ideal gas or not, the transformation can be an isotherm, an adiabatic, an isobar, an isochord, or generally a polytropic. In order to obtain ready-to-use relations for the boundary work, we start from the most straightforward case, isochoric and isobar transformations. Boundary work is 0 in isochoric transformation, while is the product between the constant pressure and the change of volume for isobar transformations. In an isotherm transformation, the exponent of the polytropic transformation is 1. From the definition of specific boundary work, and by using the relation P times V is constant, the boundary work in an isotherm transformation depends on the constant product P times V or R times T and the logarithm of the ratio between the final and initial volumes. Finally, we solved the integral by using the general polytropic expression P times V to the power of n and end up to a relation to calculate the boundary work, which can be turned in two different ways mathematically. Justification for these two expressions is given in the support material of this video. Now you know that boundary work is mechanical work from a change of volume of a controlled mass in a closed system. You know that the boundary work function depends on the specific thermodynamic transformation. By assuming the ideal gas equation of state, boundary work in several different polytropic transformations has a precise analytical function, which we have determined. Finally, you know that the net work in thermodynamic cycle is the inner area delimited by the cycle, and it can be positive or negative, depending on whether the transformation in the cycle follows clockwise or anti-clockwise.